Good afternoon, everybody. From a very cold and sometimes wet Johannesburg, they even say that we're going to get snow this week here, so very unusual weather for us. Yeah, it's a very exciting, it's the fourth webinar series in this series of now 10 webinars that we're doing in this period that we are still in lockdown, and that we basically came to the point of listen, through this new operational conditions where we're in, and through this, VUCA environment, this extreme uncertainty, volatility where we are in, we came and we put together a whole set of educational topics to cover. So what the type of themes that we see in this new operational era is, there's requirement for more remote, less eyes and ears on site, more access to secure data from a remote location, more agility. Some of our clients are scaling up and down production quite significant from 1 week or 1 month to another month. And how do you adopt to that? The constant focus of energy reduction and more sustainability has always been there. More focus on getting value from data, so doing data analytics, so more into the cloud, more looking at embedded AI, see what value we can bring from that. There's a requirement for collaboration between vendors and OEMs and system integrators and solution providers like us, in providing value solutions to our clients, which is quite important. A requirement for more virtual remote monitoring of, for example, assets like mills and crushers and pumps and fans and drag lines, so that we can see what's happening there, or even look into process. We'll see today how the team is looking at some of the technology that you can use to view and maintain a high level of processing in a processing plant. So really what we've done is we've put this whole theme together to upskill ourselves, cross-skill ourselves, all focus on really, to run our modern day operations and our assets greener, longer, safer, and faster. So you will see that there's a few themes that we basically follow through the whole time. So today we get again to advanced process control. So looking at how do I save 10% energy in my production? How do I push the yields 5%? How do I save my chemical dosing in a modern day process to about 20%, 15 to 20%. We've had sessions already on asset performance management. How do I predict a failure of assets, up to 6 weeks in advance, and what do I do with that predictions? Next week there's another session on how do I see with multivariate analysis if there's a process quality issue that I have to address, and what do I do with it? And also, we spend some time on MES already as well. How do I bring secure data to clients? How do I use it to operate a leaner, and then to bring operational reporting and technology in to bring value to the clients? So if we go to the next slide, really what we're trying to show here is in the 4Sight operational technology group, we have 3 key companies that focus on the following. So really what we do is, if you take data and you take the intelligence technology solutions that we represent, and you bring them together, you really can come and bring solutions for people. So, but always what we call intelligent, solutions. But what we have to do is you always have to look at what is the requirements for the client, and also, what is the new business models that they can adopt, to bring value to the organizations. And also there's a very, very strong drive to move more and more into the cloud. So we're constantly working with data and technology, what the client's needs are, and how do we process it. The type of intelligent technologies that we bring forward in the OT space is things like industrial IoT, or AI, machine learning, deep learning, in software that's been around from AspenTech for a long time. Things like topics like advanced analytics, multivariate analysis, all things or themes that we are basically working through in this webinar series. Simulation, and in the constraints of a plant or in the planning associated with it. How do we use virtual reality, augmented reality to make operators enabled to run the plants better? How do we keep in line with the ERP and the SAP systems at all times? So really, this technology is brought to you with 3 key entities. So right at the bottom, we have an asset automation group. which is Age Technologies, part of the 4Sight OT group, and they focus on firstly measuring, with instrumentation, installing instrumentation, measuring it, connecting to that instrumentation, taking it up to PLC or DCS layers, doing control there, making the operation safe, and then visualizing the data. They're a multi-vendor solution provider, so they take the best from Schneider Electric, Siemens, Rockwell, ABB, and bring, link to their technology, their MV, their LV, and bring the information to the next layer. So take it there. So really the next layer up is the asset optimization group, BluESP, reseller and ISP of AspenTech. We take that data and we turn it into information, knowledge, wisdom, and intelligence. So bring more value basically to that data. And then more about us a little bit later. And then there's another group in the team, which is asset simulation group, simulation engineering technology. So they focus on constraint simulation of mining and industrial processes, also focused on optimizing and planning and scheduling simulation and the control of that. How do we basically run these operations effectively? A group of about 25 industrial engineers also here from Gauteng area that is providing solutions all over Africa and also global today. If we go to the next slide, just maybe a little bit more quickly on BluESP. So we see BluESP as a very agile, dynamic company of multidisciplinary engineers. Today, I'm going to let you be in the hands of the whole group of chemical engineers that will talk about advanced process control. But yeah, we also have mechanical engineers, electronic engineers, and data scientists on our teams to bring these technologies in. We work very closely with AspenTech and see them as our road models, to bring this, intelligent technologies to us. Technologies that bring machine learning, AI, deep learning into things that we've been doing for a long time, MES solutions or advanced asset performance management solutions. And you'll hear today also how they bring some of these new methodologies into advanced process control. So really, if I look at the offer set quickly, so AspenTech has a set of design tools right at the bottom there, which focus on simulating, designing, costing, and building an optimum plant. So if I'm building a new plant today, I want to have the most sustainable plant, the greenest plant, and there's a whole set of tools that EPCs use to do that. Then if I go towards the right, there's a whole set of solutions that focus on how do I maintain assets better. So how do I predict and prevent assets from failing, and if I can predict 6 weeks in advance, what I do with that information, or how do I predict and prevent process quality variances, and so there's a whole set of solutions there. Or how do I simulate and maintenance and risk environments? So where is my key points that I have to worry about? And then the last piece is basically the operate. So aggregating the data that we have into information that I can do things with, and also then adding the operational management reporting and the method accounting or mass balancing with it, to bring value to the operations, to optimize operations of the plant. And then obviously the key topic for today is this one, optimum process control of the operations. And so with no further ado, I'm going to hand over to Dr. Kevin Brooks to tell us a little bit about himself, on the next slide, and also to introduce the speakers for today. Kevin, over to you.
Thank you very much. Welcome. It's I'm the chief engineer at BluESP. I've been working in advanced process control for about 25 years, really specializing in APC in the M, mining, metallurgy, and minerals business. But I'm not really here to speak about me. I'd like to introduce our three speakers for today. And I'm going to start with Adrian Russell. Adrian holds a degree in chemical engineering from University of Pretoria, and he also has a postgrad qualification, BEng Honours, from the same institution. Before he joined BluESP, Adrian was with Mintech, and he's been working on implementing APC solutions in milling, flotation, dense media separation circuits, as well as recently with me on boilers and autoclaves. The speaker I'd like to welcome is Suleiman Panjwani, who is the product marketing specialist for AspenTech's APC and G.Dot Solutions. Suleiman graduated from the University of Houston. We share that in common. And he has a degree in chain management with a focus on procurement and energy supply chain. He's also currently the lead AspenTech liaison for the Advanced Control and Optimization World User Group Board of Directors. This is an organization that of users who work with AspenTech to help develop the solutions. And our first speaker today, Westcott, who's a chemical engineer and has been involved in APC and process control for around 15 years. Mirinda started her career at Impala Rustenburg, where she filled various roles, including process control engineer, project manager, and plant process engineer. Before joining BluESP, she was with the Advanced Systems Group at SGS, where she implemented multiple APC projects on mining sites in Australia and Canada. Mirinda is currently the APC business lead for BluESP, and it gives me great pleasure to hand over to her to commence the webinar on DMC3 and adaptive control. Over to you, Mirinda.
Thank you, Kevin, for that introduction, and thank you, Willem, for your overview. And thank you, everybody, for taking the time to attend this webinar. The topic of today's talk is adaptive process control, modern tools for maintaining APC benefits. The core message of today's presentation is how to effectively maintain advanced process control applications and sustain their benefits. So I'm going to kick off by discussing some of the challenges that we face in achieving this goal. I will then touch on the requirements for sustaining a successful APC maintenance program. I will then discuss some of the tools and technologies we have available with a focus on adaptive process control. I will then hand over to my colleague Adrian, who will demonstrate the adaptive process control workflow. And he will then hand over to Suleiman from AspenTech, who will talk to us about adapting to new operating conditions using DMC3. So advanced process control as a technology has been around for about 30 years, and there's no doubt that it delivers substantial benefits to operations. But implementing an advanced process control system on a plant is really only the first step of the journey. Consistently maintaining these initial benefits over a long period of time is a complex process, and it can be surprisingly difficult to achieve successfully. Now, this graph is an illustration that is frequently found in the literature, and it depicts a typical life cycle of an APC application after commissioning. So an APC system is switched on and it delivers immediate and measurable financial benefits. These benefits are typically maintained for a while, but slowly over time, the controller starts degrading and it gets switched off on a more and more frequent basis. There are many reasons for this degradation. The process may change, equipment may change over time. There are changes in operating strategies, instrumentation degradation over time. And then there are people issues such as a shortage of skilled staff. Eventually, the performance of an APC degrades to a point where it has to be switched off for a revamp. Now, the time required for revamping a controller using traditional methods represents a significant lost opportunity in terms of financial benefits, because the controller needs to be offline and you lose the benefits that you initially achieved. After the revamp, the controller is put back online, and this process may repeat itself over and over until one of two things happen. The APC is either completely decommissioned or a sustainable maintenance plan is put in place and the benefits are maintained. And in some cases, it's improved. But even if you have a maintenance plan in place, it often fails. So to try and understand why this happens, let's take a closer look at a typical maintenance workflow for an APC implementation. The best way I can think of describing this workflow is by telling a story. So imagine you're a control engineer on a plant, and one of your many responsibilities is looking after an APC application. So the controller is online and everything is working fine. You check in on it every now and again. One day something changes on the process that you're not aware of, and this controller starts performing poorly. Now the operator doesn't understand what is happening or why the controller is doing what it's doing, so he switches it offline. He neglects to inform you that he's switched it offline, but he tells the following shift, the APC doesn't work anymore, and they leave it off. You discover that the APC system is offline because by chance a few weeks later when you go into the control room to check on something else. So you immediately try to figure out what is happening by talking to the operators, but by the time you talk to operators, it's already a new shift and they don't recall exactly what happened. So you start pulling data out of the database, you do some data analysis. While you're busy doing this, you get called out to do some other work because you're busy commissioning some critical piece of equipment. So it takes you a week to 2 weeks to discover what the problem is. Eventually you identify the issue and you fix the problem. But you really don't have a lot of time to monitor the controller's performance after you fixed it. So you make a note to follow up sometime soon. You tell the control room operator to let you know if there's any problems, and you rush off to your next meeting. This is just a hypothetical story, and it's based on some of my own experience. But I'm just telling you the story to highlight this typical APC workflow that is implemented on plants, and also to touch on some of the challenges that we face in maintaining APC applications. So if you look at this process, how do we streamline it and how do we make it more efficient and sustainable? We need to really look at 3 aspects, and they all need to integrate closely together. They are people, organization, tools, and technology. So the role that people play in the success of a maintenance strategy is often underestimated. The ideal, in an ideal world, you need to have a dedicated multidisciplinary APC team, typically about 1 person for every 10 controllers. However, this is becoming more difficult to achieve because of skill shortages. For mining operations, this is especially difficult to implement because of the remote location of some of the operations, as well as high staff turnovers. The APC footprint also tends to be smaller, so you cannot easily justify a team dedicated only to APC. So you will typically find either a process engineer or a control engineer who is responsible for maintaining an APC application as part of their total responsibilities. In this case, the risk increases significantly that the APC application will slowly degrade over time. If this site APC champion finds themselves in a position where they don't actually have the time to fully dedicate to maintaining an APC application. So how do you mitigate this risk? It is really all about identifying the right person for the job and then building strong collaborative relationships based on trust between this person and internal and external resources. When I talk about external resources, this could be software vendors, third-party support services who really understand the business objectives. And this collaboration should be aspects such as performance monitoring, support, continuous improvement of the application, and also, very importantly, training. So we can have another webinar just about this topic. So I'm just going to talk about the internal resources and touch on the role of operators. We all know that change management is a critical process during implementation, but it should not really end when commissioning is complete. Operators have to remain involved in the day-to-day operation of an APC. Their feedback is invaluable, and maintaining their trust in the system is absolutely essential. If operators do not trust the system or understand what it is doing, they will switch it off. And then regaining this lost trust is actually much harder than maintaining it. So this involves constant communication between the site champion about changes to the system, as well as continuous training of the operators. Once again, it all comes down to communication and building relationships. Then the importance of communication and collaboration extends into the organization as well. You need an organizational support structure where the APC strategy is aligned with your business objectives and where people from different disciplines can all be called on for support and maintenance. An APC application cannot exist in isolation, and its performance and benefits should be visible to everyone in the organization. So a high level of organizational commitment and buy-in, it really helps to maintain focus and momentum. You need to sustain an APC maintenance plan. So finally, I want to look at the tools and technologies that's available to pull this all together. So I'm going to do this by looking again at the maintenance workflow we looked at earlier and integrating the tools into this workflow. So first off, we have operate and control. This is your APC application that delivers your control and economic optimization objectives. This should be a platform that is user-friendly for both the engineers as well as the operators, and it should be easy to operate and maintain. The next step in the process is detect and alert. The technologies we are talking about here are APC performance monitoring tools that you can use to detect when the performance of an APC system is degrading. Time is of essence here. If the performance of an APC system starts declining and the issue is not addressed, trust in the system will slowly be eroded over time. So it is important that performance management system calculates the most relevant KPIs that can be used to identify where the issue may be so it can be addressed quickly. This includes systems that can analyze the performance of the underlying regulatory control layer, because this is also very important. It's also important that these KPIs are visible to the correct people. And yeah, I'm not only talking about the engineers looking after the system, but creating visibility of the APC benefits across the organization can help to maintain focus, and it ties in with the organizational commitment I spoke about earlier. So the next step in the whole workflow is diagnose and correct. And I'm going to discuss both of these steps by giving you an overview of adaptive process control. So what is adaptive process control? Adaptive process control, as implemented in DMC3, is a workflow with the objective of automatically updating models while still maintaining process optimization. To create an effective continuous process for achieving this objective, you really need several pieces of innovation to seamlessly integrate with each other. First off, you need an engine to automatically step your process to generate test data. For this, you require a robust algorithm with economic relaxation abilities to provide room for step testing while also still maintaining optimization control. After you have collected the data, you require automation to replicate human judgment when editing the data so that you can remove bad data points. As you can see on this diagram on the right here, some data has been automatically removed by the software. This requires the ability to be able to also detect PID loop status in conjunction with the data editing. So once you have a clean data set, you need to have the tools available to automatically run an model identification algorithm using this test data. You can see the one on the right here, there's a new models overlaid with existing models. Once you've generated these candidate models, you need online tools that allow you to test and evaluate the quality of these models. On the left here is an example of a model quality test you will see when using adaptive process control. And on the right here, we have an example of a model quality test available in the configuration and development environment. And then finally, when you have all these steps completed, you need a streamlined method where you can run a simulation on your model if you want to, and then the ability to configure and deploy your new models in a live environment. I'm not going to go into the detail on each of these steps, so I'm just going to look at the step testing methodology as implemented in DMC3. So DMC3 has 3 modes of operation. We have optimize and control, smart step, and calibrate. So optimize and control is your standard DMC control mode. This is where your process is controlled and continuously driven to its economic optimum point. Smart step was the first breakthrough that enabled automated step testing to be implemented. The process is moved away from the constraints and the optimum operating point, and a move plan is implemented that will ensure that all the CVs remain within their limits. This technology greatly decreased the time required for step testing, but there was the negative aspect of product giveaway and non-optimum operation, since there is no optimization taking place during the stepping. So calibrate mode was developed to address this perceived shortcoming of smart step. So calibrate mode delivers steady state optimization while simultaneously generating step test data. It does this by defining an optimization region that is close to the ideal economic optimum where the step tests take place. The size of this region is defined by what we call the calibration ratio. The calibration ratio indicates the fraction of the ideal optimization objective function value that must be achieved during the step testing. It calculates a step test move plan for each variable to ensure that this optimization threshold is maintained and the controlled variables remain within their limits. It is really a tool that enables the engineer to trade off optimum control with step testing. So it's not just a simple fraction of the total range available for stepping. You can see a calibration ratio of 0 essentially is optimum control optimization, whereas a calibration of 1 gives you basically smart step. So in summary, maintaining the benefits of advanced process control applications is typically a complex process, and it involves close integration of people, organization with advanced tools and technologies. Adaptive process control is one of these tools that enables you to bring new efficiencies to the process of sustaining APC controllers. It's a continuous background process that does not require operator intervention or the need to turn the controller offline during step testing. Optimization is uninterrupted, ensuring that the optimization benefits are not sacrificed during stepping and model updates. So that was just a quick overview, and I will now hand over to my colleague Adrian, who's going to take us through all the steps in the advanced process control workflow. Thank you, everybody, and thank you, Adrian. Over to you.
Thank you, Miranda, for the overview. So in the interest of time, this will not be a live software demonstration. However, I'll just walk through the steps of how you would implement DMC3 Calibrate on a simulated zinc flotation process to update the models. So I've configured a simulator and a controller that have been given severe plant model mismatch in order to cause the controller to oscillate. And I'll then go through the steps of using DMC3 Calibrate to produce step test data while still optimizing the process. And then finally, I'll go through how the models for the controller can be updated and deployed to the controller using the online tools. So an overview of the process, we have 4 zinc flotation cells in series with air addition points to each cell, which are automated. We also have reagent addition into the first cells. And then we have level control valves on the second and the fourth cell. The feed flow, density, and grade are all measured online, and these are the disturbances to the process. And then we also have the final tails and concentrate grades measured online. So in terms of the optimization objectives for this process, we want to minimize the final tails grade to maximize the recovery while keeping the concentrate grade within constraints. To minimize the cost, we will be minimizing the reagents addition, and we'll be maximizing the air as well, which will also ensure that we maximize the recovery. So the scenario that we're simulating is we have a flotation process that's under DMC3 control, and the collect reagent has been modified. And this has changed the relationship between the process inputs and the outputs, which has resulted in quite a severe degradation of the controller performance. And if we just have a look at what that means in terms of the simulator, over here we have the curve that represents how the controller thinks the plant is going to respond. And this curve encircled in orange represents how the plant will actually respond. So this is a model gain mismatch of 400%, which is quite severe. If we look at some time series trends of the current control performance with the model mismatch, we can see that the final tails grade is oscillating quite severely around its lower limit, which is the optimization point. And so these excursions are quite frequent and quite severe. And in response, we can see that the air addition rates to each of the cells are oscillating quite severely. You can see we have rather large input disturbances to the process for demonstration purposes. These are significantly larger than what we would expect on an operating plant. So rather than just qualitatively looking at the performance with the time series trends, we can have a look at the performance monitor and the KPI dashboard. In the performance monitor, we can see that we have a benefit shortfall of approximately $3,500 a day, as well as a controller effectiveness of only around 73%. So that effectiveness is calculated based on the MV utilization, as well as the utilized range of the MVs and a number of other factors. And then going over to the KPI dashboard, we can see that the oscillation indices for both the control variables and the manipulated variables have been flagged in red, indicating that they've exceeded their predefined thresholds. And as we saw, the airs were oscillating. So this provides a central point to see the oscillations for all the variables. And we can also see here that the prediction error for the control variables has been flagged. So this indicates that there's a large difference between how the controller thinks the plant is going to respond and how the plant is responding, which you would expect given the model mismatch in the simulator. So these are just a few of the KPIs that we can use to diagnose performance problems in the process. But it's evident from this that we need to run a step campaign to update the models to improve the controller performance. So we can access calibrate mode from the production control web server interface. So we can click on the control tab, and then we have the option to switch the controller either into test mode, which is smart steps that Miranda mentioned, or into calibrate mode. So on switching into calibrate mode, we can set the calibrate ratio, which I've set it to 0.5, because I know that I have a large model mismatch between the plant and the controller. So if I try Optimise too aggressively, I will introduce severe oscillations into the plant while I'm stepping. So calibrate ratio of 0.5 gives me, it moves the optimization away from the critical points. And then I can also set the maximum and minimum step sizes for each of the variables independently, as well as the average step duration for each of the variables. So the step-in algorithm will then calculate a step profile that fits within these bounds, and the step duration is an average. So there will be some steps that are longer, some steps that are shorter, but it will work out to 15 minutes on average. And as I said, these can be changed independently for each of the variables. So if we look at some time series trends of the plants under calibrate mode, we can see that all of the manipulated variables are stepping simultaneously and independently, and they're also making uncorrelated moves. So if we look at, I've only shown 2 of the flotation cells as set points here, but if we look, both of these manipulated variables are expected to have a similar effect on the process outputs. And here they've followed 2 completely separate step profiles. So by doing this, we will have the data that we will have at the end will be better suited to identifying independent relationships between each of these inputs and the process outputs. And we can also see that the control variables are maintained mostly within limits. So here we can see the tails grade, which has been optimized to the low limit, and you can see there's some giveaway from that lower limit, which has been targeted by the controller. With the optimization objectives, as I said, we can see that the tails grade is still close to that lower limit. These reagent additions are being minimized. They're not minimized to the lower addition limit, they're minimized to a dosage limit, which is an additional controlled variable that's not shown here. And we can see that while cell 4's air is being maximized, it's in the upper region of operation, cell 1's air has stepped throughout its operating range. In conjunction with Calibrate, we have the test agent that runs to continuously analyze the data quality. So the test agent identifies sections of data which would potentially adversely affect the modeling process later on, and it automatically marks this data for exclusion from further analysis. So these regions are denoted by the bands in this image, and these bad slices can be augmented by manual slices as well, should you identify any additional periods to exclude. So before starting with the modeling, it's useful to run the model quality analysis, as Mirinda mentioned. So here you can see the cells that are highlighted in red, which is all of them, are where the model quality analysis predicts that there's large mismatches in the gains of the identified models and the models currently in the controller. So if we hover over one of the cells, we get a pop-up, and here we can see that the estimated gain multiplier for the cell is approximately 4, which we would expect since that's what we set in the simulator. But we obviously wouldn't have this information available of what the real process model is on the plant. We would just get an estimate of the gain multiplier. Following that, we can set up a case for model identification. So here we can set the time range that we would like to do the model analysis over, as well as which variables we would like to include. If we suspect that the process time to steady state is different from the original controller, we can change it here as well as set in the maximum model order for the state space models. And upon running this case, we get this output, which shows the newly identified models in blue and the existing models in the controller in red. And looking at this by eye, we can see that there's approximately a 4 times gain difference between most of the blue and red models. But once again, rather than looking at it qualitatively, we can go to the frequency uncertainty plot for each of these models. And we can see here for most of the manipulated variable to output models, we have good certainty of the models in the steady state to middle frequency region, which is where we would expect most of the process disturbances and limit changes to occur. But then in the high frequency region, you can see we have relatively high model uncertainty, and this is due to the noise that's introduced in the simulator. Now, if we left calibrate mode running for longer, we would obtain slightly more data about this region and we get slightly more certainty, but we'll never be able to eliminate the frequency uncertainty in the high frequency region completely for a process that has noise. If we look here at this feed density model to the 2 outputs, we can see that there's poor model certainty throughout the frequency range, and that's because this disturbance is a very slow sinusoidal disturbance. So for the period of calibrate data that we have, there's not sufficient information contained in that data in order to develop an accurate model. So we will exclude that from the model updates later on. So once we've looked at the frequency plots, we can decide which models we'd like to update, and we can go on to assembling our model. So in this view, we simply select the models that we would like to update. Note I've excluded the feed density models, and you just say right click and say update curve. And then we save a new model file with the updated models. And if we click save and simulate, it takes us on to a steady state simulator. What that steady state simulator does is allow us to check that the optimization objectives that were defined originally in the controller are still achievable with the new process models that we've just obtained. So we can change the process measurements and limits to whatever we would like them to be, and check that the optimizer makes the correct decisions about the trade-offs. And once we're happy with that, we can click deploy. So this deploys the changes immediately to the online controller, and they will be implemented at the next controller cycle. So if we leave the controller running for some time with the updated models, we can see that the control performance has improved substantially. We have fewer excursions below the low limit on the zinc tails grade, and we no longer have oscillations on the air. So we can even see that the cell 2's air has been optimized to the maximum limit, and we can see that the reagent dosages are stable at those low internal dosage limits that were specified, still in response to the same disturbances that we had before. But again, quantitatively, we can go to the benefits monitor, and we can see here that the benefit shortfall is now reduced to about $1,000 a day, and we have an effectiveness of about 93%. Now, since we've just updated the models, this likely indicates that we should redo the benefits analysis for this controller so that we get this benefit shortfall closer to 0, and we now create a new benchmark point going forward. In addition to that, if we go to the KPI dashboard, we can see that the oscillation indicators for both the control variables and all the manipulated variables have disappeared. And we can also see that the model prediction error for the control variables is no longer flagged in red, indicating that our controller update has been successful and that we have improved our controller performance. So this concludes the demonstration of DMC3 Calibrate to update models rapidly online. So now it's over to Suleiman to give us a rundown of some of the other new features of DMC3.
All right, thank you so much, Adrian. I'm going to be covering 3 of our items that we have offered in DMC3. Let me get my presentation up. And let's go. All right, my name is Suleiman Panjwani, and glad to be here. I was glad to be invited to present with everybody. I want to cover a couple of our components of DMC3 that we have since V11, which are available now. And the first one I wanted to cover was SmartTune. SmartTune's patented technology allows easy controller LP tuning to match the new operating objectives driven by changing market conditions. In the absence of SmartTune, an APC expert is needed to go through a very involved process and exercise to update the LP costs, which takes significant time and expert resources.
Sorry, let me just, are you sharing a screen? We think we're not seeing it.
You are not seeing it. Let me double check that.
Well, I can share from my side if you want.
Do you have it now? Sorry about that.
Yep, now we can see it. Thank you very much.
All right. So as I was saying, SmartTune's online strategy view, it enables powerful and intuitive visualization of the controller priorities and what the controller does when it hits certain constraints. This lowers the barrier to deployment and maintenance and enables more engineers to use the technology. As this process is optimized, it is being pushed to the higher value product, which increases yield of preferred product by about 3 to 4% and reduces energy by up to 10%. Another one of our most important DMC3 application components, especially in our VUCA environment that we have now, with substantial portions of the workforce operating remotely in today's environment, gaining real-time visibility into the asset performance through secure remote access. It's a critical capability. and that's our centralized performance monitoring. It enables you to actively track and elevate your most important APC KPIs across your enterprise. The centralized monitoring dashboard provides an easy way to monitor the on-off performance and the reasons why controllers were turned off. The dashboard can also be used to track benefits of APC controllers. This is done via Aspen Watch KPIs, and it is enabled at each Aspen Watch server. The information is then replicated to the centralized server in, say, the corporate network, where users can access the performance and take actions. Maintaining peak APC benefits by accessing controller monitoring, logs, and alerts to quickly diagnose issues and reduce controller downtime. Another one that we requested to talk about was the nonlinear APC models. Starting or included in V11, DMC3 controllers support nonlinear controlled variables, and the goal for including nonlinear CVs in DMC3 was twofold: to simplify the process of building and updating nonlinear models, and to unify technologies and make DMC3 the standard for building linear and nonlinear controllers. Therefore, building a DMC3 with linear and nonlinear variables becomes a hybrid approach, where the nonlinearities are handled by DMC3 without having to develop and deploy a separate nonlinear controller. DMC3 fully supports all nonlinear models from Aspen Nonlinear Controller. The same workflow is available for building BDN custom models and etc. There's a new feature for adding nonlinear user-defined formulas. This is a significant improvement over the current custom model of the nonlinear controller. User-defined formulas allow CV to be a function of other inputs and outputs, including other existing nonlinear CVs. A sequential quadratic programming algorithm with trust regions is used for nonlinear steady-state optimization, full support for ranks, external targets, and all other DMC3 features. The DMC3 nonlinear CV also supports nonlinear variable dynamics, such as time constant multipliers, which adjust dynamic for an output to be faster or slower. All associated inputs are affected. Variable dead times, which there is a separate integer value for each output and input relationship, and gain multipliers, which is the same concept as gain multipliers for a linear controller. I also wanted to go over a couple case studies that we have. This one was with Braskem, and it covers the learnings and success from implementing an optimization strategy in Braskem's distillation columns, the deethanizer and depropanizer, using Aspen DMC3 to significantly reduce variability and energy consumption, all while keeping the process within the safety of environmental regulations. The issue that we had, the problem we were trying to solve, was the lack of optimization in distillation columns was resulting in lost potential benefits and unnecessary excess in spending on energy. And there were frequent composition peaks and excess of reflux, meaning excess utilities spent on refrigeration compressors that use high pressure steam. The approach that we took was we used plant test data to build and update models which predict the process response to disturbances, and then that information is used to stabilize production and push the process into the optimal point. These models are continuously adapted to represent unavoidable changing of the plant conditions. And we monitored, the main KPI that we monitored was the high pressure steam consumption on the refrigeration compressor's turbine. The results we got were that the total amount of energy spent was reduced by 20% per ethylene ton. And after some assistance from AspenTech on the first set of models, Braskem was able to implement Aspen DMC3 on their own with existing internal resources. In total, there were, I believe, 3 engineers working on this project, all with less than 5 years of experience. As a result of the deployment of adaptive Aspen DMC3 models, less high-pressure steam was required in the turbines running the condensers for cooling, reducing fuel gas usage on boilers, which created that high-pressure steam. And as a result of these successes, the fact that the controller design and implementation took only 2 months, Braskem plans to go ahead and expand DMC3 to additional units. Another case that I wanted to talk about was the one with Chemours, covering the learnings and successes from a project to upgrade their controller performance monitoring application and delve into criteria for evaluating the different options considered. The problem that we were trying to solve here was that limited resources to monitor critical process performance and safety parameters by analyzing information from thousands of sensors that generated thousands of measurements every minute. We decided that we wanted to identify instrumentation failures in a timely manner so that repairs could be made before it impacted production. The web interface with KPI tracking, reporting, and PID control loop monitoring capability to identify process issues proactively was implemented, and a centrally located secure server to support multiple global plant sites. This resulted in Aspen Watch monitoring functionality, helped reduce plant downtime, and it improved process control maintenance and environmental tracking and safety. And so as a result, Chemours tends to expand the use of Aspen Watch more and more widely across their businesses. Thank you so much. Back to you, Kevin.
Thanks, Suleiman. Thanks to all the speakers. I think it was a very interesting flow through this presentation. We've overrun a little, but we've got some time for some questions which people have been posting. I'll start with this one for Marinda. What is, in your consideration, the relative cost and effort that a company should consider investing to maintain the APC performance across time?
Yes, that's a very relevant question, Kevin. I think the answer is it depends. And I think it depends on the operations level of expertise, the level of internal skills they have available. If they have very low level of skilled personnel, you will require a lot more input from external support systems. So you will typically have support contracts with vendors who will come to site and spend a week on site helping you with training, etc. If you have a high level of skilled on-site personnel, then obviously you don't need to visit sites as often, so your costs become lower. So it is a, the question is, how long is a piece of string? How much money do you want to spend?
Yeah, I think that's true.
Yeah.
The next question I'm going to throw to Adrian. How would you identify which one of the controllers is affecting the overall flotation performance if a global economic performance measure is being used?
Yeah, so for each of the, so if we're talking about a process where we have a number of individual MPC controllers installed, but one common financial performance goal, each of the benefit of each controller is benchmarked independently during commissioning or throughout the life of the process. So we'll have a breakdown of each controller's performance individually. So if you have a fall off in your overall economic benefit, then it will be quite easy to identify which is the offending controller. And then we also have the ability to define a number of custom KPIs that can calculate the giveaways on different variables independently, which should make it much easier to identify which variables are result in the global economic performance degradation.
Yeah, so the individual bits of the APC are monitored by the performance monitoring in any case, but
Yes.
but the objective function for the system is for the system, and in fact it has to be, otherwise any optimum you find is suboptimal, and that's kind of the argument for not doing cell by cell optimization, because it's really not optimization. Right, and then I think I'm going to take this one myself. This kind of performance indicators, can they be used over any different AP solutions, or mainly are applied for MPC solutions? So the idea of KPIs and calculating them from values in a database, because everything about the controller is historized in the database, that is generic, and we have the tools to do it for any kind of solution. It so happens for the APC solutions, they've been pre-programmed. So we don't have to write our own KPIs, we don't have to write our own routines, but we could if we wanted to. Okay, and then I think the last question we're going to take is a nomenclature question. Suleiman, you mentioned BDNs. Can you expand on what that is?
Sorry, I was stuck on mute. The BDNs that I mentioned were part of the variables that we've looked at. I don't have full information. It's like the custom models, but I'll probably have to go back to the actual process engineers to get.
You don't have to. I'll fill in for you.
Okay.
So BDN stands for Bounded Derivative Network. So early on in the days of looking at neural networks for nonlinear control, AspenTech produced a neural network technology that could guarantee that the derivatives of the network were bounded. And this was a great advance in using neural networks for nonlinear control. And that technology is still is there now within DMC3. And I think this is of huge advantage for people who have problems that have nonlinear elements in them, because the BDN can be trained like a neural network, but it's well behaved, unlike many neural networks. I've got a last question. Again, I'm going to throw this at you, Adrian. Do you see calibrate mode being relevant in smaller applications, such as maybe you'd find in the cement industry or something like that?
Yes, so I've personally used calibrate mode in a small application. It was only 3 manipulated variables, and it was extremely relevant there. In we had a safety critical process, and we needed to rapidly develop reliable models for the controller without manually stepping the process, because we had 2 ramp variables within the process, which could become unstable very quickly. So for many smaller processes, calibrate is a good tool for shortening the commissioning time quite substantially.
Thank you very much. Well, I think we're going to wrap it up there. It's 3 o'clock. We've done it exactly on time. As you can see, we're all available to have a chat with you at any time you would like. And there remain 6 more webinars in our series. They're all on Wednesdays at 2 o'clock. And please have a look. I'm sure there's some others that will be of interest. I know there's some questions about maintenance, which we didn't address here because it was off topic, but some of those webinars will be addressing those. And also this webinar and the previous 3 webinars that we've had, those recordings are available if anybody wants to have a listen.
Thank you very much, Kevin, and thanks. I would have expected nothing else from a group of chemical engineers to bring us precisely in at 3 o'clock. So we still have another 20 seconds. So yes, 100%, as Kevin said there, you know, these events are recorded. You can refer to it again. You can share it with others. You can go to past ones. And so please do visit them again and share it with your colleagues. I would like to thank again Marinda, Adrian, Suleiman and Kevin for their preparation and for delivering this event with excellence. So that's great. A whole host of events planned still. So next week we focus on multivariate analysis, focusing on how do we control quality of the process variation better, you know, and you know, how do we predict it in scenarios where we have a huge amount of multi-data or multi-variables, and we're trying to understand what's really happening there. We are continuing with, you know, on the bottom right, with training or virtual training during this lockdown period, so you can still subscribe to either e-learning or virtual training. We're constantly doing these training courses to enable our clients to you know, configure and use this technology themselves. And like I said, through this event, our business consultants is available to engage with you either on MES or advanced process control, anything that you saw today. So you will get another email after this event. Just let us know if we need to engage with you, if you have more questions, and we can arrange a Teams call with you. So yeah, thanks for the time that you spend the hour with us. Really appreciate it, and hope to see you at one of our future webinars next week or the weeks following.